There, this is Tina, and we're going to look at the solutions to the last fake homework. We didn't have any problems assigned on this. There wasn't any homework on it, so I wanted to show you the types of problems that you might see on the final and explain solutions, so you can use this as reference at home. The first question on the fake homework is you download a file, and then I wanted to see if you remembered how to find certain experimental values on a diff pair. For example, well, the first question is explain the biasing circuitry. If you look at this circuit, here's your diff pair. Here's your diff pair, and then you've got some circuitry over here. You've got Q6, Q8, Q7, and a resistor. And it looks kind of like biasing circuitry you've seen before, but not quite. It's got these two in parallel right here. Tail current source, we know that's just a current source, and we see the diode connected transistor and the resistor. That looks really familiar. The thing to realize here is that if you have some current going through here, you only have half of that current going through each side. And so when you set the base voltage here, it has to be for half the current going through the tail. So simply what this does is, by putting two transistors in parallel, now half of the current, and so this is a one-to-one mirror here, so whatever current's going through here is going to be forced through here too, or this is going to be set to have that current too. By putting two transistors in parallel, you get half of the current going through each of these. And since only half the current's going through each of these set a VBE for only half the current. And now when you use that over there, now you're setting for ISS over 2. So if this is ISS, then you have ISS over 2 going through each of these. Each of these set their own VBE to conduct ISS over 2, and that's what you want in these guys. So that's the first question. ADM. So finding ADM experimentally, you can use balanced inputs where Vn plus and Vn minus move in equal and opposite directions, or you can use unbalanced where you pick a VIC. Since ground is the lowest voltage here and 8 volts is the top rail here, I just picked something in the middle like 4 volts. So if I put 4 volts on here and then I do an offset on this input of 4 volts, so it's going around that 4 volts, that's as good as having a balanced input for us. Okay, and that 4 volts over here, that's the average voltage, that's your VIC, that's your common mode input. So you would put 4 on here and move and swing this a little bit and see your amplitude on your output. Now remember, if you have, let's say I have 2 voltages, and in the common emitter, you compare the output to ground. So if the output of a common emitter moves this much, let's say it moves up a volt, that means that the output has changed to have 1 volt. Oh wait, so did I say? So if the output changes half a volt, then that's the total amount that your output changed, relative to ground. But in a diff pair, as one output goes down, the other one goes up. Okay, so let's see what happens here. Let's say right now this voltage is a volt over this. So here's one output, here's the other output. Now this output is 1 volt over this output. Okay, when this goes down a volt, now the voltage has changed 1 volt, but in a differential circuit, this also goes up. So you have 1 volt change and then another volt change. So even though they only moved 1 volt, even though each only moved 1 volt, there's a net change of 2 volts. So you have to actually double the gain, or double the maximum. So if this goes, so you take the maximum value, you find where, I'll just show the solutions, that's faster. It's gone. Okay, so let's do, just a sec. actually, let me change this back. And actually, let's change these. Well, it doesn't matter. Okay. Let's hope it doesn't matter. And so if this is your output, you have, here's a maximum of that, here's the minimum. So peak to peak, don't know what that is, but let's do, you can do the first cursor on one graph, and then you can do second on the other. Don't have to do it that way. And if you look at the graph here, it says 3.24 volts. So that's from here to here, but since they're changing, the output is also changing in equal opposite directions. You have to double that to actually have the gain. Okay, not sure if that was more confusing or less confusing. Okay, so that's how you would find the differential gain. You find the maximum top to bottom, and then you actually have to double that. Okay, and then for theoretical gain, the gain is the same as a common emitter, and the circuit that I gave you had an active load, so you have ROP, RON. These values, the early voltage here, that comes from the model file. The currents, you go to your simulation and see what the current is going through your circuit, and just plug in the values for that. Power supply rejection ratio, if I told you not to do any simulation or math, if the ground of, so for the tail current source, got the biasing circuitry here and the tail current source. If these grounds are close together and have the same noise on them, this is almost entirely rejected. As these two move together, this node is kind of works like a hinge, because this one doesn't care what its collector voltage is. So this can move up and down a little bit without really affecting that. So power supply rejection ratio should be, rejection ratio should be really high. So I'll fix that before I post this. Let's put that in red. Okay. Common mode is, and this is again going to be a little bit surprising if you simulate. Common mode rejection ratio means if you change the average of the inputs, how much does the average of the output change? And in this case, it actually changes more than you would expect, and that's because you have these active loads that are really sensitive. When you change your average here, you've changed your VCE of Q1, which by base width modulation increases the current a little bit, and then because of the increase in current, these are really sensitive, these two transistors here, and the output will actually move more than you expect. If these were resistors, then your common mode gain would be pretty close to zero. Okay, common mode gain, and then the common mode rejection ratio is just your differential gain over your common mode gain. There's that. Okay, so the most important part of this, these are the questions that we haven't practiced in class that I do want you to be responsible for on the final. So let's see what we're doing here. This is just finding capacitances at nodes. So I gave you 3 circuits here, and the first question is, what is the capacitance at this node right here? Okay, so what you have to remember is that if you're sitting on this node, you go in all directions on the wire, not just forward, not just backwards. You go all directions you can possibly go until you run into a transistor. And so thing to remember is, okay, for a MOSFET, MOSFET, you have, if this is the drain, sorry I can't spell very well, and this is the source, this would be the gate. Remembering this diagram right here will help you the most with these kind of questions. Okay, so that's supposed to be a G. Okay, so let's see what the question is here. The question is, wants to know the capacitance at this node right here. So if you go up, you hit a drain. So that means you're sitting here. And on the drain, you see two capacitors. You see the drain to substrate, or drain to bulk, so dB. You also see the gate drain overlap. So the capacitance looking up would be gate drain overlap and drain bulk. Okay, looking down, you hit another drain. So again, you're sitting here and you see what capacitors you see if you're sitting on the drain. You see gate drain overlap, you see drain bulk capacitance. Okay, so then you come out here and you hit the gate. So that means you're sitting up here. That means you see 1, 2, 3 capacitors. See gate drain overlap, see gate source overlap, and you see gate source. Remember, this is coupling to stuff in the channel, but just by convention they call that source capacitance. Okay, so the answer to that is you've got your drain bulk of this transistor, you've got your gate drain overlap of that transistor, you've got your drain bulk of this transistor, you've got your gate drain overlap of that one, and then you have your gate drain overlap here, and there's a gate source capacitance, but notice that it's not in this equation. Give you a second to think of why that is. Remember, this is a follower. So on a follower, if V out moves 1 volt, what happens to V out 1 moves 1 volt, what happens to V out? It should move the same amount. So if there's no voltage change across those two nodes, the capacitance, you can ignore it. So that's what this says right here. There's no change in voltage across the capacitor, so you get to ignore those capacitances. Okay, second question was for circuit 1 V in. So I'll find circuit 1 V in. Was it V in minus? Doesn't really matter, but V in minus. Okay, so now we are sitting right here, and that means you're sitting on the gate. So you come over here and you sit on the gate, you see these 3 capacitances. Okay, so that seems really straightforward. You know, if this circuit is a differential circuit, this node right here isn't moving. So any capacitances to the source, those are just whatever they are. Okay. So gate source is whatever these capacitances, their values. There's nothing you have to do with them. It's like the other side of them are connected to ground. So that's just the value. Okay. Now this gate drain capacitance, that's something else. This is in the cascoded case. And in the cascoded case, when V in minus goes up, that's just changed the VGS of this transistor. Okay, so if this goes up, VGS increases, the current through here increases. Now this transistor here, it's got a DC voltage on its gate, but since the current through it's increased, physics takes over, and physics moves the source voltage down to increase the gate source voltage to the same thing as this. So if you move V in up, VGS of this transistor is increased, the current through here is increased, so the current through this transistor is also increased. The way this transistor increases its current or changes its node voltages so it can accommodate that current is by increasing its VGS. But since the gate voltage is fixed, the only way it can change VGS is by dropping the source. Okay, so the source drops the same amount that V in goes up. And so what you have here is V in goes up a certain amount and this node goes down a certain amount. So what you actually get is you get a 2 across that capacitance. So what you see is the gate source overlap, since this is basically a ground here, and then you get see the gate source, and then this capacitance to the drain, that gets multiplied by 2. The node here is going down by the same amount that Vn is going up. Okay. All right, so let's see, 3. The third one is circuit 1 V out. Okay, so the capacitance on this node right here. Okay, so this is a follower again, and you're sitting on the source, so you go over here and you see, okay, I'm sitting on the source, I've got a source bulk, I've got source gate overlap and a source gate. Okay, so you go over here and you say, okay, source bulk is at ground, so that is just whatever it is, and then you've got the capacitance from the gate and source, the 2 capacitance across there overlap and just the regular one. We're on C, was it? Yeah. Okay, so the one's gate source right here, both sides are moving together. There's no voltage change across that capacitor, so it disappears. So the only one you see is the source bulk. So that's that. Okay, 1D. Okay, here's circuit 2 and asking for V out. So V out, if you're sitting here, you need to go in all directions to see what you hit, and up, it's just a resistor, so that's you assume that there's no capacitance there ideally. And then here you're hitting the collector. So now you have to go to model of a BJT. Supposed to be an E, B, C, and a substrate. And you know that there's 3 capacitances, BE, BC, and CS. Okay, so let's go back over here. For V out, that's sitting on the collector. So if you're sitting on the collector, you see 2 capacitances here. Collector, substrate, and base collector. Okay. And base collector is often called C mu. So this is C mu. And this is C pi. And that's just CCS. Okay, so if you're sitting on the drain, just go right over here and say, so if I'm sitting on the, collector, I see C mu and CCS. Okay, now we have to see if there's anything special going on. Okay, so the collector to the base is ground. So there's nothing special to do there. The other side isn't moving. And then the other one is collector, substrate, and the substrate is ground. So there's nothing special here. And it should just be collector, base, collector, substrate. And there's no Miller effect because you're sitting on the output. Oh, but that's a common gate, so base, so it doesn't matter. Okay, 1E. V in for circuit 2. So V in for circuit 2. Now you're sitting on the emitter. Got to go back over here. If you're sitting on the emitter, the only thing you see is a C pi or CBE. Okay, so C pi or CBE. And now you have to say, okay, is the other side of the capacitor moving? No, it's not. So it's just that value. So it should be just CBE. 1F. Okay, V out of circuit 3. So here's circuit 3 and asking about V out. And we actually already did that problem. Nothing different from the common base right here. You're sitting on the collector, so you see the collector substrate, which is to ground, and you see the collector base. Right here, the base was truly ground. Over here, because it's on the output of the amplifier, when you look across the capacitor, the other side looks like it isn't moving because it's moving 1 over AV times as much as the V out is moving. So it almost looks like this is a ground. So you just take that capacitor as its value. So there's the capacitance on the output here is basically the same. And you should just get, let's see, CB and CCS. Okay, last but not least, V in. CV in of circuit 3. So now, of course, we have to have one example with the Miller effect. So if you're sitting on the base, let's go back over here. If you're sitting on the base, you see these two capacitors, one to the emitter and one to the collector. Okay, so let's see. The one to the emitter's not moving, so that's just whatever value you have. So there's the CBE. Okay, the other one, V in to V out, that's CBC. Other side's moving a lot, you get the Miller effect, so that capacitance has to be multiplied by 1 plus AV. Okay, and remember AV for a common emitter is just your GMRO, so you can plug that right in. Okay, so remember the rule is so you find your capacitance, and if the other side of the capacitor is moving, then you probably have to do something special with it. If it's cascoded, you multiply by 2. If it's across a follower, you get rid of it. If it's across a gain stage from the input of an amplifier to the output of the amplifier, you've got the Miller effect. If it's going to ground, then you just use the capacitor value. Okay, and then I just for your, oh, I forgot about this one. Okay. Then great, we found capacitors. The reason we're trying to find capacitors is to find poles. So here's circuit 4, and I put a bypass capacitor in here, which means this node doesn't move. Okay, bypass capacitor quiets this node, and it sits there. If this wasn't there, then the calculations for this particular circuit would be much more complicated. The first one is find the poles and zeros at the base of Q5. Okay, so what you need to do is at the base of Q5, I should have gotten rid of this coupling capacitor too to make this clear. I won't have a coupling capacitor there on the exam if I have a circuit like this. But if you're sitting on the base, and you go over here, you say, okay, what's my capacitance? If I'm sitting on the base, I've got these two to the emitter and to the collector. Is the emitter moving? No, because I have the bypass cap, so that's just CBE, that stays the same. And CBC, yes, you've got the Miller effect, so you have to Miller effect, so you have to multiply it by 1 plus AV. Okay, to find the pole, it's 1 over RC, so we just found the C. To find the R, you look at, and again, I'll get rid of this capacitor. You look in all directions, front, back, up, down, and see your resistances. Yeah, okay, your resistances. And right here you have R3. Since this is a DC source, it's going to be an AC ground. So you have R3 to ground, you have R4 to ground, and then you have this R in to ground. And right here, actually I should get rid of, let me think about that. But you have, if you look at R in at low frequencies, then you have R pi plus 1 plus beta times R1. And there's your R pi plus R1 times 1 plus beta. And then it's all three of these in parallel because all of them go to an AC ground. And then to find the pole, it's just 1 over this over R times C. Okay, at V out, if you've seen the video, you've seen that you get a 0 when you're at the output, and you can just memorize that it's GM over C mu. That's the only one we're going to see, GM over C mu. And for the pole, you have R looking up, which is R2, and R looking down, which is just RO, because we have this at an AC ground. The capacitance here is you're at the collector, so you go back over here and you say, if I'm on the collector, I see C mu and CCS, so CB and CCS. To the base. Base is the input to the amplifier. It's not moving much, so you can consider it an AC ground. So those are just those capacitors added together. That's how you find a pole. And we have one more circuit here. I think I'm going to let you, just if you have questions, the answer's on here, but it's the exact same thing. You find the capacitance in a node, find the resistance in a node, it's 1 over that R times C. And again, even though this is a MOSFET, and that was a BJT, right here you're going to have a 0 looking back, and it's just going to be the same thing. This GM over C, it's not C mu anymore. Remember, C mu is from the base to the collector. It's gate to drain on this one. Gate to drain on the MOSFET. So I'll leave that one for you to do. The answers are there. Oh, and this is what I was going to say. Just for your future reference, and it's not going to be on the exam, I put in, if you wanted to calculate the values of these capacitances, actual numerical values, I gave you the equations, and I gave you values to use in them, so you can calculate about what the capacitance would be. And this is from an old homework. I just cut and pasted it in here, and I can get you answers too for this. And then there's the random 4. But this is just for your reference. Let me put an exclamation point on that one. Let's make it all bold too. Okay, so that's how you find the R's and C's. That's the quick method. And then the slower method is the analysis that's on the video. Okay, thank you.